So the example, let's take let's take an example first of all. Let's take x to the power of 1/2. I mean square root of x, square root of z, as an example. So now if you look at this, so this is the same as r. I mean z is r times e to the I theta. So it's square root of that, right? Which is square root of r. R is a positive number. Square root, when I say square root of r, I mean I take the positive value of square root of r. And e to the power of I theta by 2. Right? Now if you look at the, so suppose z is some point here with some angle theta. Okay. Now as you move around and move this point around the origin, and you come back, so theta will go to theta plus 2 pi. Right? So in that case, what's going to happen to this? So when I move around the circle, so theta goes to theta plus 2 pi, right? This will go to square root of r times e to the power of I theta plus 2 pi by 2, which is e to the square root of r e to the power of I theta by 2 times e to the power of I pi, right? Which is minus. Okay. So you see this function, what it is saying is this function is not single valued. As you come back, it picks up a minus sign. Right? However, suppose I take another closed curve, something like this. Suppose I go around like that. Okay. In this case, nothing is going to happen because as you go around, theta is going to increase up to the maximum value here. Right? But then again, theta is going to decrease and come back to its original value. Right? So theta will not go to theta plus 2 pi along this path. Along this path, theta will come back to itself, which means the square root of z will come back to its original value. Right? So you can convince yourself that any path, any closed path that you take which does not go around the origin, the function will come back to its original value, no matter what kind of a curve you choose. Something like this, for example. It is not passing through the origin, I am passing around the origin. So once again, you see theta increases. Maximum value of theta is like this. Then again, it starts going back and comes back to its original value. Right? However, any path which goes around the origin, theta will come back not to itself, but theta plus 2 pi. And then you will pick up a minus sign. Right? So this point, there's something special about this point, right? Because we are talking about paths which are going around this point or the paths which are not going around the point, right? So the paths which are going around the point, the function comes back with a minus sign, right? Whereas any path which goes not around this point, the function comes back to its original value, right? So this point is called the branch point. You can do the same thing for, say, z to the power of 1 over n, where n is some integer. You do the same thing. This is the same as r to the power of 1 over n times e to the power of I theta divided by n, right? So now if you take a path around theta plus 2 pi, this is going to pick up a face e to the power of 2 pi I over n, right? So that's the definition of branch point here. And branch cut is so in this particular example, you see there's another branch point. This is one branch point. There's another branch point, and that's at infinity. Because if you want to look at the infinity, you remember you have to make a coordinate transformation. You have to do inversion, right? So if you study at infinity, what happens? Let me call this function f of z. Okay. Then what you have to do is to take z, write z equal to 1 over z prime. So when z goes to infinity, z prime goes to 0, right? So in the z prime coordinate, you should study what happens around z prime equal to 0, right? But if you do that, then this function becomes 1 over z prime to the power of 1/2, right? Which is the same as 1 over r prime. If you write in the polar coordinates, z prime equal to r prime times e to the I theta prime, then you get square root of that and e to the I theta prime divided by 2. And once again, you see if theta prime goes, if you take a path which goes around z prime equal to 0, you pick up a face, because theta prime goes to theta prime plus 2 pi, right? So infinity is also a branch point. And you can, what you do is the branch cut is some line which connects the two branch points. Okay. So the idea is to, you can choose any line. I mean, could be any complicated line, but I mean, as an example, suppose I choose this line all the way, the positive real axis, right? So this is going from 0 all the way up to infinity. So you just, this is a cut, which means what you're doing is you're basically cutting it, right? And considering multi-sheets, Riemann sheets, you put another sheet on top of it, so that once in the first sheet you come here, but then you don't go back to the first sheet, you go to the second sheet. Then again go around, and when you come here, you get back to the first sheet, for this example. Right? Whereas for this example, you have to put n sheets. Right? And each time you go around, you go to the next sheet. Finally, from the last sheet, when you go around, you come back to the first sheet. So this is done so that in this big space, the function becomes single valued. Right? This is a trick. This is a trick to enlarge the space so that the function becomes single valued, and then you can use all the theorems that you know of, right? Cauchy theorem, residue theorem, everything you can use in this big space, though. Right? Any other, yeah.
Do we have non-integer poles of non-integer order?
Do you have what?
Poles of non-integer order, non-integer order.
A pole of integer order.
No, non-integer.
Non-integer order. Yeah. For example, this is a, well, it's not a pole. I mean, you don't call it a pole. I think you're just asking whether it's sort of a positive square. I mean, this is z to the power of plus half. Whether you could have z to the minus half. Yeah, that's perfectly okay. Yeah.
So, yeah, you can have poles with.
It's not. You wouldn't call it pole. Pole, by definition, is something which has only integer powers, right? It will be again a branch point. I mean, there will be again a branch point if there's any power which is not an integer. Whether it is positive or negative, it doesn't matter. Say plus half or minus half, it doesn't matter. It will be multi-valued functions. Right?
So you say z should be 1 and n is single valued.
It's not single valued. No. It's multi-valued. I mean, this is just this is a special example. This is n equal to 2, right? This is after all z to the power of 1/2, right? That is just n equal to 2. But I'm saying that you can generalize it to any n. I mean, and actually, this is still a rational number. You could even make it irrational number. Okay, irrational number. Of course, then you will need infinite number of sheets, because it will never come back to itself, right? If it's a rational number, then after a certain number of sheets, you will come back to its original value, right? For example, here, if you go around n times, right? Then theta goes to theta plus 2 pi n. And then you see that the function comes back to its original value, right? Because when you shift theta by 2 pi n, this doesn't pick up any phase, because it's e to the power of I 2 pi n divided by n. That's the extra piece. N cancels, and you just get e to the I 2 pi, which is 1, right? So after going around n times, you come back to its original value. That means that you need n sheets so that this function becomes single valued. However, suppose you consider z to the power of some r, where r is some irrational number. Okay. In this case, you will need infinite number of sheets, because it will never come back to its original value. Right? But in reality, I mean, when you use all these Cauchy theorems and so on, basically you just restrict yourself to one sheet, right? And you do all your calculation in one sheet, like when we did this multi-valued integrals. We just worked with one sheet. Of course, the answer should be independent of which sheet you choose. And there you have to be careful. You have to fix a sheet, and then you know what is the range of theta in that sheet, and you work with that range. I mean, I think in some examples we worked out, we just picked up one sheet, and I told you try to do it in another sheet and see if you get the same answer or not. Right? If you have not made any mistake, you should get the same answer. Anything else? I think you have one more tutorial. Was it today or I don't know? Today there was. Okay. You shouldn't be too nervous about the exam. Okay. It's. I mean, if you have done homeworks, basically you should be able to do well. More or less, the questions will be of the same type. Yeah. Sorry.
Gamma function, is it going to be asked?
Yeah. I mean, gamma function. Okay, let me just say that. What are the most important things to remember? I mean, remember not just for the exam, but in the future when you're doing, other courses or research and so on. So there are some important things about gamma function. One of the things is that when gamma of z, when z is a positive integer, then it is just a factorial. So let's see. I mean, so gamma z, remember, was defined as, now I don't remember one of the integral representation was 0 to infinity, t to the power of z minus 1, e to the minus t dt, right? I think yeah, correct. And then there is another integral which was, this is defined only for real z positive, right? This was, otherwise, you see at near t equal to 0, there is a problem. If this condition is not satisfied, then at t equal to 0, there will be a problem, right? I mean, it's not well defined. It will be divergent. That's the reason for this condition. However, there was another integral representation, which let me see. Yeah, it was 1 over gamma z is equal to 1 over 2 pi I e to the power of t to the power of z dt. Along this path, which is because you have to choose. Z is arbitrary, right? So it's not necessarily integer or anything like that. No, in that case, there's a cut at t equal to 0. I mean, there's a branch point at t equal to 0 and t equal to infinity. So we choose a cut in the negative real axis. So this is 0. That's the minus infinity. The negative real axis, and the path is chosen to be this path. Okay. And so this integral is defined for any value of z. I mean, this is completely right. So here it's only for real z greater than 0. This is for all z. For all z, this integral is well defined. And then later on we showed that these two are the same. I mean, in the regime, in the region where real z is greater than 0, this definition is the same as that definition. We showed that. But now, what are the important points? One, that gamma of n for n positive integer is equal to factorial n minus 1. Right? That's a very useful thing. In some sense, you may think of gamma function as kind of, it's not exactly what I'm saying, but you can think of it as like kind of writing down an analytic function, right? A generalization of the factorial to an analytic function, an analytic or meromorphic function. Actually, there's a poles, so meromorphic function. But if you know this, if you remember this, then immediately you see that this satisfies the following condition: gamma n equal to n minus 1, gamma n minus 1. This follows the definition of factorial. And now, in fact, this property turns out to be in general true, meaning not just for z equal to n, but this property is in general true. In other words, gamma of z equal to z minus 1, gamma z minus 1 for arbitrary z, which you can prove directly from either from this definition or that definition, right? By partial integration. You can prove that. For example, to start from here, what you do is that you want to reduce the power by 1 unit, right? I mean, if you started from gamma z, you see on the other side it is z minus 1, gamma of z minus 1. So you want to reduce the power by 1, right? Which means I want to take a differentiation here, right? But in order to do that, by partial integration, I have to write this as a derivative of something and then do a partial integration. So this is nothing else but minus d by dt e to the minus t, right? This is the same as that, because if you take a d by dt of that, you pick up a minus sign, which cancels that, right? So once you write this, and then you do a partial integration, right? And if the boundary terms do not contribute, then you see this will hit there, and it will just give you z minus 1, which is that, times t to the power of z minus 2, right? Which will give you gamma z minus 1. Similarly, you can also prove it from there. Right? Yeah. I mean, here you want to reduce the unit, power by 1 unit, right? So write this as d by dz, d by dt of what you can write this quantity 1 over t to the z as d by dt of 1 over t to the z minus 1 divided by z minus 1 with a minus sign, right? And then again, you can do a partial integration. This hits there, and it just doesn't, it gives you nothing, just 1. But there's a minus sign in the partial integration that kills that minus sign. And you just get, so you get the equation 1 over gamma z equal to 1 over z minus 1. Gamma z minus 1, which is the same relation as that. So this is one, sorry. Yeah. Yeah. Integration by parts, yeah, correct. Yeah, exactly. So yeah, so here when we wrote this, you substitute that back here and then write integration by parts, correct? Yeah. Sorry, when I said partial integration, I mean integration by parts, yeah. Okay.
We get there 1 over gamma of z is a z plus 1 times, I think, yeah, it's not a z minus 1. But we can go back to this equation.
Now let's say isn't that true? d by dt acting on that will give you minus z minus 1, which will kill this, and then 1 over t to the power of z, right, which is that. No? I mean, after all, what is this? Is t to the power of minus z minus 1, right? So d by dt acting on that will give you minus z minus 1. There is already there is a minus z minus 1 here, right? So this kills, and then you'll get d by dt acting on that will decrease the power by 1, right? So it will give you t to the minus z minus 1 minus 1, yeah, and then this minus 1 cancels that. So this is true. Then you put that back here. So this is 1 over 2 pi I. Okay, there is a minus 1 over z minus 1, right? That this comes out because I'm not integrating z, I'm only integrating t, right? And then you have e to the t d by dt of 1 over t to the z minus 1 dt. So when you do a partial, integration by parts, you'll get this minus will go away, and then you just get 1 over gamma z minus 1. Yeah. Okay. What else then? So this is one important point. Then the other very, very important relation was, this appears in many places. This beta function, definition of beta function, it was gamma of A times gamma of B divided by gamma of A plus B. This is called beta function, which obviously depends on these two numbers. These A and B are complex numbers in general, right? But the point is that this is itself is given by, in several ways you can write it. Well, one of the ways to write this as 2 times, one way to write it as 0 to 1, t to the power of a minus 1, 1 minus t to the power of b minus 1 dt, right? Okay. This is under the condition a real part of a and real part of b both are greater than 0. The reason is that because in order to prove that, we use the that integral representation, which was valid only for real z positive, right? So it's for this reason. And then, or you can write it in this form, 2 times 0 to pi by 2 sine to the power of 2n minus 1 theta, 2a minus 1 theta, and cosine to the power of 2b minus 1 theta. Okay, there are various ways of writing it. That's okay. But one consequence of this thing was this important formula which says gamma z times gamma 1 minus z is equal to pi divided by sine pi z. Okay. So that's the this is an important formula because it immediately tells you it gives you the information about the poles. Where are the poles, right? Because you see this has a pole at all, for whenever z is an integer it has a pole, right? What this means here is that whenever z is 0 or a negative integer, I mean whenever the argument of gamma is 0 or negative integer, you have a pole. Okay? Because for positive integer we already know this is finite, right? It's a factorial for a positive integer. So if you take z equal to say a positive integer, say n, then you have a gamma n times gamma 1 minus n. And that is infinite here, right? But gamma n is not infinite. So what we are saying is gamma 1 minus n is infinite whenever n is a positive integer, right? And that implies, so for example, when n equal to 1, gamma of 0 must be infinite, gamma of minus 1 must be infinite, and so on and so forth. So whenever, so gamma of z has poles at z equal to 0, minus 1, minus 2, etc. Sorry? When z goes to infinity, here. Okay, that will that you know that is a growth, exponential growth. I mean actually much faster than that, even faster than exponential growth from the Stirling formula, right? So it's not a bounded function. So even if you take z say in the positive real axis, take z to be real, positive real, and take it to infinity, it blows up. So at infinity it blows up actually, right? So it's not a bounded function. Okay. So this formula is very useful because it not only tells you where the poles are, but if you want to compute the residue, you can use this to compute the residue at all these poles, right? So for example, I mean the way to use this, suppose I want to look at the pole at z equal to say minus n, where okay, at z equal to say minus 3. Let's suppose I want to compute the pole, the residue at z equal to minus 3, right? So what I will do, I can so to residue is what? When you make an expansion, suppose I make an expansion of gamma z around this point, then you make a Laurent expansion because there is a pole, right? So the coefficient of 1 over z plus 3, right? This coefficient, whatever that, this is what we call d minus 1. This gives you the residue, right? Sorry, one more thing. You see, immediately you see this always a pole is the first order pole, right? It cannot be higher than that because so if I take z equal to minus 3, then this guy is gamma 4. Gamma 4 is something finite, factorial 3, okay, 6. Huh? That is something finite number. But on the right hand side, it's only a first order pole, right? Because sine of z, so let's write it down. So let's write it in this way. I mean, after all, 1 over, I mean, sine of pi z plus 3 is the same as sine pi z times, I mean, this is 3 pi, right? So 3 pi is 2 pi, so it's a minus sign, right? So this is the same as, I mean, this is 3 pi plus 3z, right? Sine of 3 pi plus 3z. And sine of 3 pi plus anything is a minus times the sine of the same thing, right? So this is that. So, and now if I look at, so I can replace the sine pi z by minus sine pi z plus 3, right? And now you're looking at the situation where z plus 3 goes to 0, right? because we are looking at z near minus 3. So when z plus 3 goes to 0, so this one as z plus 3 goes to 0 behaves like pi times z plus 3, right? Because sine for a small argument is sine, if you make an expansion of sine, right? It starts with the linear term, then the cubic term, then the fifth order term. But of course, when it's very small, the linear term dominates, right? So this behaves like just pi times z plus 3. Okay, the minus sine pi z behaves like that. So therefore, this right hand side I can write as minus pi divided by pi times z plus 3 plus higher order corrections, right? I mean, there are this, if you write the full thing, it will be minus pi cube over factorial 3, 6 z plus 3 cube, etc. Right? That is what it will be, right? But for small z plus 3, this is what it is dominant. You can ignore that. I mean, of course, if you want, you can just take out pi over z plus 3 and make an expansion of the remaining part, right? But the leading term is simply this term. That's the only singularity. I mean, there is no singularity worse than first order pole, right? And furthermore, you can immediately compute the residue. So what is the residue? So this is the same as minus 1 divided by z plus 3 plus regular terms, right? When you expand it. On the other hand, the right hand side gives you, we are looking at z near z plus 3, I mean z near 3. So z near 3, this becomes gamma of 4, right? Gamma of 4 is factorial 3. Okay. So what we are seeing is that factorial 3 times gamma of z behaves like that, right? So the residue is simply minus 1 over factorial 3, right? Divide by factorial 3 both sides. So you get the residue at z plus z equal to minus 3 is minus 1 divided by factorial 3. In general, you can see if you take z near minus n, where n is some non-negative integer, then all you have to do is to do it for z plus n goes to 0, right? In that case, you can use this here, and you see that this is simply gives you minus 1 to the power of n here, right? Because when n is even, nothing happens. When n is odd, you pick up a minus sign, right? So you get a minus 1 to the n. So this will become minus 1 to the n. This is n, right? And now here is minus 1 to the n, z plus n cube, etc. So leading term is that. Whereas on the right hand side, you get here it's this z is minus n. So this becomes 1 plus gamma of n plus 1, which is factorial n. So you get factorial n times gamma z. Behaves like that. The leading term. I mean, of course, if you want to look at the subleading terms, then you must also expand these guys. Okay, but I'm only looking at the leading term because that's enough to compute the residue. That is because it's a first order pole. If it was not if it was higher order pole, you need to go beyond the leading term to find the residue. No? But here we are lucky because it's the first order pole, so you just have to take the leading term. So therefore, the pole you see residue is simply minus 1 to the n divided by factorial n near z equal to minus n. So that's okay. So that was one thing, and finally the last thing about gamma function which was important was the Stirling formula. Okay, that was right. So the formula this formula we obtained by using the example which we worked out in this saddle point approximation, right? We worked out an example, and that example gives you the Stirling formula, and that says that gamma of z plus 1 for z going to infinity behaves like square root of 2 pi times e to the minus z times z to the power of z plus half. Okay. This is a very rapid growth. I mean, it really blows up very rapidly, even faster than the exponential. Right? because this is e to the power of this I can write it as e to the power of log z times z plus half. So it's even faster than this exponential growth. This Stirling formula we will use later when we discuss hypergeometric functions. I mean, in the 4th chapter, we will use this thing. Because by using this, see what happens is that if you have a power series, let's say, for a function near some point, say there's a Taylor series or something near the point. Now, it may happen that this function has some singularity at some other point. In particular, it becomes multi-valued. It's some branch point at some other point. I mean, far away from the point where you are expanding. No? So now if you look at the expansion, can you figure out what kind of a branch point exists? No? And in order to do that, for the case of hypergeometric functions, we'll see that because hypergeometric functions, the coefficient of the Taylor series depend on gamma functions. I mean, they are expressible in terms of gamma functions. Okay? And then from that, you can estimate where the branch points are and what is the order of the branch point. No, I mean, what is the multi-valuedness and things like that. You can, by using this. So I will use that later. But it's an important formula in general, not apart from this application, because as I told you, it appears in statistical mechanics and everything, because gamma functions, factorials, have to do with the probabilities. No? So this is an important estimate, actually. I think basically these are the main things about the gamma function. Right. Okay. Anything else? I mean, if you want to define it that way, you can, but I mean, it is infinite, right? I mean, at least if you want to say a factorial negative number, I will define it to be the gamma function, the negative number. But okay, it's infinite at that point anyway, right? I mean, exactly the negative integer, it is infinite. But when you talk about meromorphic functions, you are interested in what is happening nearby, no? Not at that point only, but nearby, to see what is the nature of the pole, first order pole, second order pole, etc. No? So you should be a little bit away from exactly the negative integer. No? Yeah, so then you have to go to the complex, I mean, nearby points, no? Not at that. Yeah.
When it is negative non-integer.
Sorry?
Negative non-integer.
Yeah, negative non-integer, it's all finite. There's nothing else. You see, if z is not an integer, right? Then this is right hand side is perfectly finite, right? So for example, let's say z was equal to minus 1.5. This is finite, right? And so this is gamma of minus 1.5 times gamma of 1 minus, so gamma of 2.5, right? But that gamma of 2.5 is a finite quantity. I mean, we don't know, it's not a factorial or anything, but it's something finite. So this is a finite number times gamma of minus 1.25 is finite, right? So gamma function is finite everywhere else apart from negative integer and 0. Everywhere else is finite. Of course, at infinity it blows up, but I mean excluding infinity. I mean, in some sense, yes, I think so. I think you can say that it probably is essential scalar, because if I make a coordinate transmission, z goes to z1 over z prime, right? So then in the z prime, so z prime equal to 1 over z, you see it will have, and we are looking at z prime equal to 0, right? That is where the infinity in the original z plane is. But we know that gamma function of So we are looking at gamma of 1 over z prime, right? Whenever this 1 over z prime is a negative integer, gamma function blows up, right? Which means whenever z prime is minus 1 over n, it blows up. So there are, I mean, from this, when you come from this side, there are infinite number of points where gamma function, I mean, there's an accumulation point here, right? I mean, see, if you look at this sequence of points, right, it has an accumulation point which is 0 itself, right? So in the near 0, in arbitrarily small neighborhood, there are infinities. No? So yeah, that's yeah. Any other question? If not, I can start with, I can go on with the orthogonal polynomials. Okay, so let's see. So last time we introduced we did two things. One was a Weierstrass theorem. Weierstrass theorem basically which says that in a finite interval, any continuous function can be approximated arbitrarily precisely by polynomials. And therefore, polynomials provide a basis. So 1, x, x square, x cube, etc. This will provide a basis because you can express any function to arbitrary accuracy as a sums of x to various powers. No? Polynomial is that. No? So that was the Weierstrass theorem. And then we went on to, but those are not necessarily, I mean, if I just take x to the n, they will not be orthogonal with respect to each other, right? Because the issue of orthogonality also depends on the choice of the weight function, right? Then we, instead of going through this orthogonalization procedure, which in principle you can do, I mean, given a weight function and the interval, in principle you can go about doing it step by step, no? But it's a very cumbersome thing. So what we did was we used a slightly different approach, I mean, completely different approach to start directly constructing the orthogonal polynomials. Okay. So approach here is a bit different. So we are first constructing the orthogonal polynomials for an arbitrary w, not an arbitrary w, with some conditions, and then we'll determine the weight function, no, which will allow that. So the point was, yeah, so this was the Rodrigues formula. So let me remind you, the Rodrigues formula was Cnx was equal to 1 over w. W is a weight function, dn over dxn times w, acting on w times s to the n, okay, where n goes from 0, 1, 2, etc. Where w is a weight function, and s of x is at most quadratic. In x. And it had to satisfy a few conditions. So this was one condition. I mean, this was one condition, which is, I think it appears in the notes as the second condition. Okay. The first condition was that when you define like this, the C1 is linear in x. This is a very strong condition. Because obviously, I mean, if I just take an arbitrary w and even if I restrict myself to s being at most quadratic, right, it's not guaranteed that when you compute this, the result will be, for n equal to 1, the result will be a linear function, not obvious, right? So this is an important condition actually on w. Yes. So this is the first condition, second condition, and the third condition had to do with the boundary conditions. And the condition was that w a times SA equal to WB SB equal to 0, where we are looking at x in the interval a to b. So at the end points of the interval, the product of W and S vanish. These are the three conditions. And with these three conditions, we showed that these Cn x's were orthogonal to each other. They are not necessarily still orthonormal. We have not normalized it to 1. I mean, right? But what we have shown with this is that Cnx with any polynomial Pm x wx dx equal to 0 when m is less than n. This is any polynomial. And furthermore, we also showed that Cnx is a polynomial of degree n. These are the few things we showed. I mean, we went through the proofs of these statements last time. Okay. If you want to make it orthonormal, then you have to, because after all, you see, in this definition, I can anyway multiply by any number, any constant. It doesn't change, right? If I multiply, say, Cn by some constant, let's say Kn, and let me use this convention that they are using here. Yeah. So suppose I can always multiply by some constant, Kn. Kn is a constant independent of x. All these are functions of x. But Kn is a constant. That is not going to change these relations, because constant just comes out of the integral, right? So you are free to multiply by any constant you want. If you want to make it orthonormal, then this constant should be chosen such that the integral of Cn square times w is 1, right? But normally in the literature, you don't find this these are normalized to 1. I mean, their norm is not normalized to 1 usually in the literature. They just choose some convenient constants, which are not necessarily normalizing the length square equal to 1. But it's up to you. I mean, it's not important. That any constant you can multiply. So we will relax the orthonormality condition. Okay, we'll only demand that the Cn and Cm are orthogonal to each other when n is different from m, right? But not necessarily that the length squares are 1. Okay. So now what today? But is there any question on these two things? These are the two main results last time. Is there any question on that? I mean, both of these things are obtained by basically just doing partial integrations. You know, when you plug in here, first of all, this w cancels with that w, and then you start doing partial integrations. If m is less than n, then you see when you take n derivatives acting there, it vanishes, right? But of course, in that process, you will get boundary terms, and to make sure that the boundary terms don't contribute, that is where you use these equations, essentially. Okay, so now what we'll do today is to analyze these three conditions and see what is allowed, right? I mean, these are restrictions on W, S, and the interval actually, AB. Because interval why? Because you see this has to be satisfied at the boundary points, right? So it will. It is so these conditions are restrictions on W, S, and the interval. Okay. Okay. So let's analyze these conditions. So first of all, let's look at the C1 condition. So by just say, let's forget this Kn for the moment. I mean, let me just forget it, because this we'll put in the end, some convenient choice of constants. So C1 is simply 1 over W, and I just take one derivative, n is 1. So there will be two terms. So there will be W ds by dx plus dw by dx s, right?
Sir, how do we discover those functions?
How do we?
We discover these functions, these polynomial functions.
I don't know historically how Rodrigues came up with this. Yeah. I mean, in some sense, it is natural, right, to think about something like this for this reason. No, first of all, you have 1 over W which cancels at W, right? Then, if you have something which is a total derivative n times, right, then it's right. Then it's I mean, almost it's like one of the first things you would think about if you want to do, right? I mean, then you have to, of course, make sure that this is nth order polynomial, right? That is what gives the restrictions on both these conditions, S and C1 linear. Okay, so S is quadratic and C1 is linear. That ensures that this is at most nth degree polynomial, right? And then this n partial integrations, integrations by parts kills that, right? Okay. So, I mean, in some sense, then you have to make sure the boundary terms don't contribute. So there are all these conditions.
Okay, but I'm not able to get the inside.
The intuition, why? The intuition.
Yeah, I mean, it's okay.
Yeah.
We pose those conditions and then we do and then we make them. But that's not the problem. I'm not able to get the inside.
Yeah. I mean, you see, this is not all the orthogonal polynomials can be expressed in this way. This is only a certain class. A certain class of polynomials, orthogonal polynomials only. But I mean, to me, it looks like, yeah, it's the kind of natural thing to do. Okay, so we want that this is linear in X. Now, what I will do is I will just take this to be minus X. I mean, in general, it could be anything, alpha X plus beta, right? Linear function. But by choosing, you see, by shifting the origin of X, okay, and scaling the X, you can always make it to some standard form, minus X, right? I can always scale, because by shifting X or multiplying X by a number, I'm not going to change the degree of the polynomial, right? If I start with the nth degree polynomial in my original X, I can redefine my X by a linear transformation, right? That's not going to change the degree of the polynomial, right? So I will just choose a standard form by appropriately, suitably, changing the coordinate system, right? A linear transformation only, not quadratic and so on. Because if you take quadratic transformations, then it will change the degree of polynomial, right? You don't want to change the degree of polynomial. So only linear transformation. So I will do this. So then, so this is obtained by a suitable linear transformation of X. Okay. So then let's rewrite this equation as an equation. Okay, just so let's write it as an equation for dw by dx. So you find from this dw by dx times S, okay, this is equal to w times C1, which is minus X, plus ds by dx. Okay. So this is an important condition, important equation for w, right? This is an important equation for w. So we'll start from here. So this is I have just implemented the first condition, that C1 is linear, and as I said, by a suitable change of linear transformation, I can always bring it to this form. Sorry, this is minus. So it's minus on the side, because I had to take this on the other side. Right? So, okay. So let's now look at this equation. We said, okay, now let's go to the second condition. We said S is at most quadratic, right? So there are three possibilities. S could be a constant, S could be linear, or S could be genuinely quadratic, right? So let's take these three cases one by one and see what are the implications of that. Okay. So first case, so S is a constant. Okay. So we first look at this, and then next one we'll take S to be linear, and then next one S quadratic. So first I'll look at this. Well, in this case, ds by dx is 0. So since it's a constant, okay, let's call it S equal to alpha. Alpha is some constant. Okay. Substitute that there, so you find alpha dw by dx equal to minus wx, because ds by dx is vanishes. Okay. So now this can be easily solved, this integral. I mean, this differential equation can be easily solved. W is nothing else but e to the power of minus x square by 2 alpha. Right? I mean, you can write it like this. Divide by alpha, divide this by w. So this is nothing else but d log w by dx, whereas this is equal to minus x by alpha. So which means a log w is minus x squared by 2 alpha up to some constant factor. But constants will not be important. So therefore, w is that. So this is what we find. So w is this, and s is this constant. So you see, for s equal to constant, this is the only possible w you can choose, right? With respect to which these polynomials Cn's are orthogonal, right? But we still now have to look at the third condition. Third condition is that product of w and s vanishes at the two boundary points. So what is w times s? S times w is nothing else but alpha times e to the minus x squared by 2 alpha. Where can it vanish? It can only vanish at x equal to plus or and minus infinity, right? So this vanishes at x equal to plus or minus infinity, right? Which means our boundary A is minus infinity and B is plus infinity. So it's a full, all the complete real line. Okay. Now we can further, I mean, change this, make this, I mean, you can just, by changing the variable, x goes to x, I mean, you can absorb it inside, right? You can write x, just to simplify it, forget about alpha. X goes to x root 2 alpha, right? Then this 2 alpha can disappear, right? So you can just take w to be e to the minus x square, okay? And s, again, you see s is not important. The reason is, remember, Cn is equal to 1 over w dn by dxn, the w s to the n. Now, this alpha, I can just put it equal to 1 because anyway, these constants will just come out, right? And remember, we have anyway this ambiguity of 1 over kn, right? All those constants I can absorb in there. So I can as well put w equal to 1 and, w equal to e to the minus x square and s equal to 1, okay? So that's the first thing. So this case corresponds to, so let me just write down, in this case, I can just choose s equal to 1, w equal to e to the minus x square, and the interval is minus infinity plus infinity. The resulting polynomials are the Hermite polynomials. These are the polynomials that you have studied in the harmonic oscillator problem. Okay. These are the Cn's are usually denoted by Hn in this case, just because it's Hermite polynomials H. So this is Hermite Hn equal to simply that. So if you substitute this is okay up to some constant 1 over kn. This is simply e to the power of x square dn by dxn e to the minus x square, because s is 1. So this is the Hermite polynomials. Any question on this? Because then I will go to the next stage, which is S is linear. I will go to the next one. But before that, is there any question here? Yeah. No, as I said, I mean, this is irrelevant, right? Because if you put here alpha, this is just alpha to the n, which comes out, right? And that can be absorbed in the kn, because kn was arbitrary anyway. So it can be just, so I can as well put alpha equal to 1. It doesn't matter. Right. I mean, just to give you to see how it's working. So if I just let's look at the first few guys, h0 n equal to 0, there's no derivative, this cancels that, and we just get 1 over k0. h1 is one derivative, so this will give you minus 2x, right? And then times the exponential itself, which cancels that. So you get here h1 equal to minus 2x divided by k1, and you can go on, and you can see that h2 will be two derivatives, so there will be several terms here. I mean, so d by dx to the minus x square is minus 2x to the minus x square. Now d2 by dx2 to the minus x square is, you take one more derivative there, so there are two possibilities. The derivative can hit here or there, right? When it hits here, it will give you again minus 2x, so that gives you 4x squared. And when it hits here, you just get minus 2. So 4x squared minus 2 times e to the minus x squared. So h2 is simply 4x squared minus 2 divided by k2, and so on. And you keep going like that. So these are the Hermite polynomials, up to an overall constant. I mean, in the quantum mechanics application, you try to normalize them, right? So that kn then is determined by normalization condition. But at this stage, we don't worry about that. Yeah. I mean, it may not be, maybe you cannot, maybe in the harmonic oscillator problem, you have seen it in a different form. I don't know. But it is, by suitable changes, you can map this to the harmonic oscillator problem. Okay. Maybe later on when I discuss the differential equation that these guys satisfy, maybe I'll try to comment on that. Okay, what else now? Yeah, now we go to the, no more questions here? If not, then I can go to the next point. This was s equal to constant. So let's look at the next one. Yes. Yeah. So now let's look at S linear. So S is linear. S equal to, say, alpha x plus beta. So it's a linear function. So substitute that here. So you get alpha x plus beta dw by dx equal to minus w alpha x plus beta. No, x plus ds by dx. ds by dx is simply alpha, right? Okay. So therefore, again, I can do the same thing. dw by d log w by dx is equal to minus 1 over alpha times x plus beta times x plus alpha here. Right? I just divide by this and divide by w. So you get that. What is this? This is minus 1 over alpha is outside. And here I can add and subtract a beta, right? So x plus beta divided by x plus beta is 1. And the other remaining thing is plus alpha minus beta divided by x plus beta. And now we can integrate. So log w is minus 1 over alpha x minus, I'll make it plus beta minus alpha times log x plus beta. Integrate this up to a constant again. Again, constant will not be important for us. So w therefore is e to the power of minus x by alpha times x plus beta to the power of beta minus alpha. Okay. Now what about, so far this is fine. So again, we have taken the linear function and then solve for W. Remember, this was the content of the first equation, that C1 is linear. The first condition gave you that. No? So now with this choice of W, we have made sure that C1 is a linear function of x. But now we have to still worry about the boundary conditions. Okay? So what is W times S? W times S, just multiply this with that. So up to a constant is e to the minus x by alpha times x plus beta to the power of beta minus alpha plus 1, right? Because this times that gives you beta minus alpha plus 1. Right? And you want this to vanish at the two endpoints. Okay? So at one endpoint, I mean, if x equal to minus beta, this will vanish, provided this power is positive. Right? If this number is positive, then at x equal to minus beta, this will vanish. Okay? But that's all. You can only find one point. Other point is, of course, if alpha is positive, then you can take this vanishes at x equal to infinity. Right? So you see there are two places it vanishes. One, at x equal to minus beta, provided this is positive, beta minus alpha plus 1 is positive, right? This vanishes. And the other is x at infinity, it vanishes if alpha is positive. If alpha is negative, it will vanish at x equal to minus infinity. Right? But so I can just choose alpha positive. Okay. Fine. Once again, by choosing the freedom to make a linear transformation on x, we can bring it to some convenient form. And you can make such transformation. Let's write x plus beta divided by alpha is some new x, is some, let's say, x prime. In that case, S becomes alpha square x prime, and W becomes, see, x plus beta. So this becomes up to some constant, it just becomes e to the power of minus x prime times x prime to the power of beta minus alpha. I mean, here you can just put plus beta and minus beta. X plus beta divided by alpha is x prime, so that is the e to the minus x prime. Other term is just a constant. And similarly, here you can multiply and divide by alpha. So you get x prime to this thing and then some constant together. So all this is absorbed in the constant. And again, constant is irrelevant because you see W appears in the numerator and denominator in the definition of Cn, right? So these constants just drop out. Right? I mean, the Cn was defined as 1 over W d and derivatives of W times s to the n. So if you multiply W by a constant, it doesn't matter. And again, this constant is also irrelevant because that can be absorbed in the Kn. Okay? So I can as well put this constant is 1 and this also is 1. Okay? And then what is the range? You see, x was minus beta, but that means x prime is 0. So here the range is for x prime is between 0 and infinity. These are the Legendre polynomials, the ones you studied in the hydrogen atom problem. Okay, in hydrogen atom problem, you studied the associated Legendre polynomials. This is just Legendre polynomials. Okay. So then, therefore, we conclude. So what we have, in this case, we can just choose s equal to x, W equal to e to the minus x, x to the power of some. Let's call beta minus alpha as some nu. The main condition is beta minus alpha plus 1 should be positive, which means beta minus alpha must be greater than minus 1. So this nu must be greater than minus 1. Okay. So this with this condition, I think people, because of Legendre, probably they use L, I don't know. L, yeah. So these are called L, N, I mean the corresponding polynomials L and mu is up to some constant Kn. It's simply this thing, 1 over W where S is this and W is that. And these are called Legendre polynomial, nth Legendre polynomial, but it obviously depends on nu, right? Because there's a parameter here, nu. So the only condition is nu should be greater than -1. Apart from that, there is no other condition. Okay. You can also make sure that with this, because the W better be integrable, right? I mean, it better be that this integral exists from the lower limit to the upper limit. It should exist, right? It should be finite. So here the lower limit is 0, upper limit is infinity, and W is that. So this is e to the minus x, x to the nu, where nu is greater than -1. So you see this integral is well behaved at both infinity because this exponential suppression, and at origin also is well behaved because because of this condition, nu is greater than -1. So this integral is finite. So this is the Legendre. How do you pronounce Legendre? L-A-G-G-U-E-R-R-E. Okay. I am just implementing those three conditions. First condition implied that, then you choose for different possibilities for S, solve the differential equation for W, right? And then ask a question where this vanishes, S at W vanishes. That tells you the interval. So the procedure is very clear, right? Okay, so now the last one where we take S to be.
Yeah, what happens if alpha equal to 0?
If, sorry?
Alpha equal to 0.
Well, alpha equal to 0 then is a trivial thing. I mean, then there's nothing. I mean, S is 0, right? Then, I mean, it's everything is 0 then. You see, I mean, in this, if S is 0, everything is 0. So you don't get anything. You just get a trivial, right? Okay. Fine. The last one now. When S is genuinely quadratic. So let's see. So S is quadratic, so let's write it as well, alpha times x plus beta times x plus gamma. Okay. I'm not following exactly these notations. Or that is I mean, I think here this is gamma and that maybe that is alpha, something like. But anyway, it doesn't matter, right? So okay, so we do this again, and let's try to solve, plug it in there. So I get here alpha x plus beta x plus gamma times dw by dx. Actually, let me bring the w on the other side, so that this is 1 over w, which means d log w is minus x plus the derivative of this ds by dx. So which is, so there are two terms. Okay, there's alpha, of course, and then you have, when it acts here, you get x plus gamma, and when it acts here, you get x plus beta. Right? So plus x plus beta. So that's what it is. So therefore d log w by dx is equal to, and now we have to bring this on the other side. So this, we have to do this partial fraction. So okay, this part is easy. So let me first start with that. So minus this alpha cancels there, so you get 1 over x plus beta, and then minus 1 over x plus gamma, right? When you take this part and divide by this, x plus gamma cancels, and you just get 1 over x plus beta. Whereas if you divide from this, you get x plus beta cancels, you get that, right? But then we have this, which we have to So we have to again write it in terms of partial fractions, no? Okay. So how shall we do this? I mean, let's look at this. Let's write this as a divided by x plus beta plus b divided by x plus gamma, and we want to determine a and b, right? So you get, when you write it as a common factor, so this is the same as x plus beta x plus gamma times a x plus gamma plus b x plus beta. And now you compare it with this. Look at the linear term in x. It's a plus b. The coefficient is a plus b. So one condition is a plus b equal to minus 1 over alpha. 1 over alpha. And the other condition is a gamma plus b beta is 0. Right? So I think I can erase this because I don't need this equation anymore. So how will you solve this? So substitute, for example, I don't know, b is equal to minus 1 over alpha minus a. Substitute that back here. So you get here a gamma minus b over alpha, minus, 1 over beta over alpha. And then minus a beta. Equal to 0. So that tells me that a times gamma minus beta is equal to beta divided by alpha. Implies a is equal to. And then if we substitute that there, then b is equal to 1 over alpha comes out, you get minus 1 over alpha comes out, you get 1 plus beta divided by gamma minus beta. So this time beta cancels. So this is the same as minus 1 over alpha times gamma divided by gamma minus beta. That's good. Okay. So now we can integrate. So w, log w becomes, you have to include also minus 1 here. So you get here log of x plus beta, log of x plus beta multiplying minus 1 plus, what is x plus beta? This coefficient a, right? So plus a, which is plus beta over alpha times gamma minus beta. This is multiplying log of x plus beta. And similarly, log of x plus gamma. Coefficient is again, there is a minus 1 from here. And then b, which is that, so is minus gamma over alpha times gamma minus beta. So this is the weight function. I don't know if I made some mistakes here. No. But at the end of the day, it will be some number times log of x plus beta plus another number times log of x plus gamma. Those numbers are, okay, in order to get these numbers, I went through this, but it could be that I have made some mistake. I don't know. If you found any mistakes here? I don't know. Minus 1. It looks okay. I think it's okay. I think it's okay. Huh? Okay. So therefore, we can integrate this, and we find that w is x plus beta to the power of this number. Okay. Let's call this number mu, and this number mu. So x plus beta to the power of mu, and x plus gamma to the power of mu, where mu and nu are these numbers. So right here. And mu is minus 1 minus these two numbers. Okay, so that is the solution. If I choose S to be this, then W is that. in order to ensure that C1 is linear. Now finally the boundary condition. So you see we have to look at S times W, where S times W will just give you x plus beta up to some constant. Constant is not important. X plus beta to the power of mu plus 1 and x plus gamma to the power of mu plus 1. Right? And we want this to vanish at the two endpoints. And that will happen if mu and nu both are less than mu plus 1 and nu plus 1 are greater than 0. Right? It will happen at x equal to beta, minus beta, and x equal to minus gamma. Okay. So if you choose if mu and nu are greater than minus 1, so that mu plus 1 and nu plus 1 are greater than 0, then this vanishes at x equal to minus beta and x equal to minus gamma. So this will be my interval, minus beta to minus gamma. Okay. Now again, we can, this looks a bit cumbersome, so we can again make some linear transformation to bring it to some standard form. And the linear transformation I can make is something which say puts minus beta equal to minus 1 and minus gamma equal to plus 1. After all, these are just the two endpoints. I can just choose by suitable coordinate linear transformation. I can put the endpoints anywhere I want, right? This is finite. This is of course finite, not infinity. So I want to choose the endpoints as minus 1 and plus 1 instead of minus beta and minus gamma. Okay. So this I can do by a coordinate transformation. Let's say x, what shall I say, x plus beta. So x, maybe I should just look at this. What was the definition? Yeah, 2x. So x plus beta plus x plus gamma divided by, say, beta minus gamma minus beta. Let's say. Let's try that if it works. So when x equal to minus beta, you see this vanishes. You get here gamma minus beta. So maybe I should put here beta minus gamma. Okay, let's put here beta minus gamma. So this becomes gamma minus beta divided by beta minus gamma. So x equal to, so let's call this x prime. Okay. So x equal to minus beta corresponds to x prime equal to minus 1. And when x equal to minus gamma, this vanishes. This you get beta minus gamma divided by beta minus gamma is plus 1. So x equal to minus gamma corresponds to x prime equal to plus 1. Right? So in the x prime variable now the range has become a standard range, minus 1 to plus 1. Right? And when you do that, you can show that, so what is going to happen? In the x prime variables, this should just become, you see, S is a quadratic polynomial which has a roots precisely this minus beta and minus gamma, right? But in the new variables, the roots are x prime equal to minus 1 and x prime equal to plus 1. So S must simply become x prime, x prime square minus 1. X prime minus 1 times x prime plus 1, which will be x prime square minus 1. Up to some constant. This constant is irrelevant, so I can forget about this constant. And W will become x plus 1, x prime plus 1 to the power of mu, and x prime minus 1 to the mu. Okay? In the x prime variables. Sorry. It's just a linear transformation. Say I wanted to, this is the boundary points, right? Minus beta to minus gamma. I want to make a linear transformation so that the boundary becomes a standard boundary, minus 1 and plus 1. Right? And for sure such a linear transformation exists because after all, by just a shift you can move one point to any other point, right? So if I'm given an interval, let's say suppose minus beta is here and minus gamma is here, and you want to, for example, bring this minus beta to minus 1, right? I can just shift this whole thing by a suitable amount to bring it to minus 1. Suppose I just shift this whole thing, right? This interval there. So this point will come there and that point will come there, right? But that's not enough. I want to also make this minus gamma to plus 1. So then I can just take this, okay. You understand what I'm saying. It's possible always to make the interval by scaling also. I'm also allowed to scale. No? So you can scale, and so this is a precise linear transformation. Right? This is a linear transformation because there is a x times a constant plus a constant. Right? This is a linear transformation. X prime, this is equal to 2x over beta minus gamma plus beta plus gamma divided by beta minus gamma. So some constant times x plus another constant. It's a linear transformation, and with that what we have achieved is that indeed explicitly you can see that when x equal to minus beta, x prime is minus 1, and when x equal to minus gamma, x prime is plus 1. So you have, by linear transformation, you have brought the interval to minus 1 to plus 1. Okay. This is just for convenience. It's not, it could be anything, right? Okay. So this is so the last category this was, so we take s equal to x square minus 1. W is x plus 1 to the mu, x minus 1 to the mu, with a condition mu and mu greater than minus 1. And that's it. So, and this defines you they're called Jacobi polynomials. Jacobi polynomials. And you see there are two parameters now, not just one parameter. For Legendre there was only one parameter. Now there are two. Yeah. You had a question? No. And these are denoted by, let me see, is denoted by P for some reason, En, and you have mu nu x. These are the Jacobi polynomials. So there are two parameter family of polynomials. Okay. In fact, the way it's written is more like this. Put here 1 minus x to the mu. Okay. And also you write this as, again up to overall minus sign, this is the same, 1 minus x square. Okay. And this is better to write like this because you want this to be a positive number, because mu is arbitrary, right? Just mu is greater than minus 1. It doesn't have to be an integer, right? Could be any number. So it better. So you want to take a positive value, right? If you write it as x minus 1, there's a problem because the range is minus 1 to plus 1. That's the interval. If you write it as x minus 1, you see this can be negative, right? And then negative to power of some non-integer number is a bit of a problematic. You have to look. It's a branch cuts and so on. No? So you have to worry about the faces and so on. Yeah? So that's why it's always better to write it like this. Okay.
Can we choose beta and gamma to be equal?
Sorry.
Beta and gamma.
No, then of course it's not possible. Yeah.
Okay.
Then then the interval becomes just a point essentially.
Yeah, but when we start, we say we have beta and gamma. But if we set down beta to be equal to gamma, then
yeah, then let's see. Then you cannot. Then you have to redo the whole thing because at several places I divided by beta minus gamma, right? So you have to redo the whole thing then. Yeah. First of all, the partial fraction won't be. Here when beta is different from gamma, we could always write this thing as some number. Let's say a divided by x plus beta plus some b divided by x plus gamma. But if the two are equal, you cannot write it like this. No, it will be. At best, you can write it as some. It will be. There will be also, if beta equal to gamma, you will have a term which will be some b divided by x plus beta square, right? Yeah. In that case, when you integrate, it will be different form, completely different form. Yeah. And actually, there is no solution. In fact, it turns out for that. Yeah. Solution meaning which also you want to also make sure that s times w is 0 at 2 points. No, then it turns out it's not possible. Now, Jacobi polynomials depend on two parameters, and there are special cases which you are probably familiar with. In fact, it's listed here. I am not going to go through all that. It is listed in page 208. There's a table. In particular, look at the second entry, the Legendre polynomials, which you have again seen. Legendre polynomials. And that corresponds to the case where you choose mu equal to nu equal to 0. It's very simple. W is simply 1. Then, right? So in this case, W is simply 1. And S is 1 minus x squared. So that is the Legendre polynomials. You have seen that in the context of spherical harmonics, I think in quantum mechanics, right? When George explained to you spherical harmonics, it was multiplying this. There were two angles, theta and phi, right? Phi is the azimuthal angle, and the theta is the angle which goes from north pole to south pole, right? So the azimuthal angle dependence was very simple. It was basically e to the power of I times some integer times phi, right? And then there was a function which depended only on theta, and those were called associated Legendre polynomials. Theta is basically you write x as sine theta or cos theta. X is cos theta, let's say, or sine theta, doesn't matter. Then S is 1 minus x squared, so it's sine squared theta. Right? So everything can be expressed in terms of theta. And this is not the associated Legendre polynomials, these are the normal Legendre polynomials. And that corresponds to choosing m equal to 0. If m equal to 0, it's the same as normal Legendre polynomials. Yeah, so there are lots of, so all of these things you see just comes from the generalized Rodrigues formulae, and you see also you can see the proof that they are orthogonal to each other. No? I mean, this gives you automatically an orthonormal basis of functions. Okay, now I've got, let's see. In this table there are listed various choices. I mean, but okay, they don't appear, at least as far as I know, they don't appear so much in the physics literature. The Gegenbaur and Chebyshev and so on. I don't think they enter so much. Legendre enters a lot. But clearly there are two parameters, so you can specialize to various values and define your own polynomials. Okay. Now it's because I think these polynomials came earlier than the generalized ones. These came in the particular physical applications, but then people realized that there's a more general class. So, okay, now what I would wanted to show, I think let's say 15 minutes maybe. Two things. So this is all the complete classification of the Rodrigues polynomials. Of course, this is, as I said, there's no claim that this is the. I mean, this is only a class of orthogonal polynomials, okay, which can be obtained in a very systematic way. That is the nice thing about it. It's obtained in a very systematic way. But now these polynomials, I mean, in general, okay, this polynomial satisfies two things: certain recursion relations and certain differential equations. Okay, so I want to discuss that. First, the recursion relation or recurrence relation. Okay. This relates various CNs for different n's. Okay, so in particular, the claim is that there will be always a relation of the following type: Cn plus 1 of x is equal to something, let's say Anx plus Bn times Cn x plus C plus Dn Cn minus 1x. Okay, where An, Bn, and Dn are constants. So what it is saying, it's saying that it's a relationship between three consecutive Cn's. See, this is a relation between Cn minus 1, Cn, and Cn plus 1. So three successive C's. There's a recursion relation like that. Okay. This actually is true not just for this Rodrigues polynomials. It is true for any orthogonal polynomials. Okay. So how to see this? So let's see. So what is remember what is the n? This n just means it's an nth degree polynomial, right? This is n minus 1th degree of polynomial. This is n plus 1th degree polynomial. Right? So first of all, I mean, this has a n plus 1th, I mean, this has a term x to the n plus 1, right? Obviously, because n plus 1th degree polynomial. So there will be a term inside here which will be like x to the n plus 1 times some coefficient, which let me call it kn plus 1 coefficient, plus the lower terms, but there will be such a term. Similarly, Cn is an nth degree polynomial, so it will contain a term like x to the n times some coefficient kn. Let's say, let me use the same symbol, yeah, kn, right, plus the lower terms, right. This one starts with the x to the n minus 1, okay. So this one will have a kn minus 1, x to the n minus 1, and lower terms, this guy. So if you look at here, I mean, you want to, you have to reproduce x to the n plus 1 somehow from the right hand side, right? So the way, from where it comes, there's x to the n here, but that is multiplying also this linear function in x. So x times x to the n will give you x to the n plus 1. So that tells me immediately that an must be equal to kn plus 1 divided by kn, right? So that the x to the n plus 1 matches on the two sides. Okay. Okay. So let's consider this combination then. So let me do the following. Let me take this part on the other side, the first term, just this part on the other side. So let me consider Cn plus 1x minus kn plus 1 divided by kn times Cnx. So what I have done, I've just taken this term on the left hand side. Okay. So what is the property of this? The main property is that the x to the n plus 1 has disappeared. Sorry, x times this. That's the x is also there. X to the n plus 1 has disappeared from here, right? I mean, we have chosen this constant precisely to cancel x to the n plus 1 term. Okay. That means this is a polynomial. This is a polynomial of degree n. Right? This combination. So that means I can expand it in terms of some coefficients, let's say am, cm, x, where m goes from 0 to n, because this is nth degree polynomial. This combination is nth degree polynomial, so I should be able to expand it in this basis, right? Where m goes from 0 to n. Okay. So if you look at now this statement, what we are saying is that, I mean, I've taken this on the other side, right? So what is left over here? This and that, right? So what this statement is saying is that actually in this sum only two terms contribute, the m equal to n and m equal to n minus 1, right? Everything else must disappear, everything else must vanish. That is what this statement is saying. Okay. So we want to prove that that am equal to 0 for m between 0 up to n minus 2, right? That's what we want to prove. So that there will be only two terms here, m equal to n minus 1, which is this, and m equal to n, which is this term. Where, ams of course are constants. Right? Ams are constants. Because I'm just expanding. This is an nth degree polynomial, I'm expanding in terms of this basis of polynomials. And so these are just constant coefficients. Okay, so this is what you want to prove. So how will we prove that? So let's see. I mean, how will I compute am? Well, if I want to compute am from here, I just multiply this by cm, right? And integrate with multiplying w times cm and integrate both sides. So multiply Let me, okay, both sides by ck x times wx for k between 0 up to n minus 2 and integrate. Okay. So when I do that on the right hand side, because they are orthogonal polynomials, the only in this sum the only term which will contribute is when m equal to k, right? So right hand side gives you ak times the normalization, whatever the normalization is. So we call it hk. Okay, hk is by definition this norm length square. Hk is ckx square times wx dx between in the appropriate interval. It will be some number. Okay, I just call that. It's certainly a non-zero number, right? Because this is positive, that is positive, everything is positive. So this is certainly a non-zero number. Okay, so right hand side gives you that. What about the left hand side? Okay, can I erase this now? I mean, this was the, so I mean all this, this statement is now summarized in this statement. It has no more information there. Okay. So now let's look at the left hand side. So what we are doing is we are multiplying w times ck times cn plus 1, cn plus 1. Okay, let me put here x minus kn plus 1 over kn x cnx integral a to b. Okay. Okay. So let's look at the first term. This is clearly 0 because k is between 0 and n minus 2, and that is n plus 1, and these are orthogonal. So the first integral vanishes. Okay. The second integral, you have a cnx and then a ckx times x. This is a constant, so I can take it out. But ckx times x is a polynomial of degree k plus 1 at most. I mean, in fact, k plus 1, right? But if k is up to n minus 2, right, then k plus 1 will be up to n minus 1, right? So whatever this times that is going to be some polynomial of degree less than or equal to n minus 1, correct? I mean, take what is it, ckx times x, right? Take the x here, multiply that. So this is a polynomial of degree k plus 1, right? Because there's a x, I mean, this is k degree polynomial. I'm multiplying by x, so it's k plus 1. But k is less than or equal to n minus 2 here, right? So k plus 1 is less than or equal to n minus 1, right? So you have this time multiplying with the cnx, right? So what we have is cnx times some polynomial which is of degree less than or equal to n minus 1, and I'm integrating, but that is orthogonal, I mean, it vanishes, right? So this integral also vanishes. So left hand side is 0, right? So what have I used? I've used that the Cn is orthogonal to any polynomial of degree less than n, right? That was the crucial part of that. So that means right hand side is this, left hand side is 0, and hk is not 0, so therefore ak must be 0 for all k between 0 and n minus 2. Now, of course, I mean, I'm not going to go through this. So this is true. So what is left over from here is simply a n minus 1 cn minus 1x plus a n cnx. So I need to only determine these two numbers on the right hand side, and that can be determined again. Just multiply by cn minus 1x wx and integrate. So if you take this, if you take now the same formula but for k equal to n minus 1, right? If you take k equal to n minus 1 here, this will become nth degree polynomial. Okay. So then I should be able to get, I mean, once you know that what is the normalization of Cn, what is the Cn square integral, then which I was calling Hn. No? So this can be determined. These numbers can be determined by knowing the information about the normalizations and this coefficients case, and the same thing with that. So this can be determined, and that's be determined in the notes. In terms of these numbers, this case, this kn plus 1, etc., as well as this h case. Okay, is determined, but it's not so important. I mean, really, the important point is that on the right hand side there are only 2 terms, and that tells you that there is a recursion relation between 3 successive c's. That's the important point. This can be used, for example, in quantum mechanics problem. Sometimes you may want to look at expectation value of something, right? Say position x. You have some wave function and you want to look at the expectation value of x. So then you want to take x times, you have to multiply, or matrix elements of x. No? Say you have an nth state and a kth state, and I want to look at the matrix element of x. So then I have to put x, cn, ck, right? So that will give you, I mean, all sorts of physically interesting quantity. Or you may want to look at x square. So then you have to use the recursion relation twice. No? Things like that. So it's useful. Yeah, because this tells you, you see that x times cn can be expressed in terms of cn plus 1, cn, and cn minus 1. You know? So then you can put it back and then use orthogonality condition to compute. So it's useful for quantum mechanics application. Now, the differential equation, I don't know, should I do it now? Okay. Yeah, so let's, okay, it's a 2-line actually. I mean, our details are not, details I'll do tomorrow, next time. I mean, the specific cases, case by case. You know, the Hermite polynomials, all those cases. But I'll just try to do a general statement. Then. So remember, for this recursion relation, I have not used the Rodrigues formula. All I've used is that there is orthogonal polynomials. We don't know from where we got it. We are not using Rodrigues. We didn't use the explicit form of the Cn, which appears in Rodrigues formulae, right? Here, the only thing we used is that Cn with any polynomial Pm, Wx dx is 0 when m is less than n, right? This is the only thing we have used here, not the details of the Rodrigues formula, right? But the differential equation, for that we will use the Rodrigues formula. Okay? The idea here is this: take this function 1 over w d by dx acting on SW dCn by dx. Okay. Now you remember, okay, so let's see. First of all, let's look at the degree of this polynomial. This will be some polynomial. Let's see the degree of this polynomial. This is a degree n, but I'm taking a derivative. So this is degree n minus 1. This product. Now remember that this one of the lemmas that we used in proving that Rodrigues polynomials gives you their orthogonal was this lemma, which says, it is in page, is equation 10.2, right, which says that dn over dxn acting on w s to the n and any polynomial of degree less than or equal to k is equal to w s to the n minus m. Where is m? Sorry, this is m. Then polynomial of degree less than or equal to k plus m. Right? This was the lemma which we used to prove already. Now let me divide both sides by w. So this becomes here w. And apply this for m equal to 1. Okay? And n equal to 1. Right? So if I apply for m equal to 1 and n equal to 1, you see that 1 over w d over dx acting on w s times polynomial of degree less than or equal to k is s to the n minus m, n equal to m equal to 1. So that is, this is 1, and that is a polynomial of degree less than or equal to k plus 1, because m is 1, right? So now apply this here, but this is a polynomial of degree n minus 1. So when I apply this, this is going to give me a polynomial of degree n. I mean, of degree n. Right? At most degree n. Which means I can expand it again. So this means that I can write this as some combinations, let's say ak, ck, x, where k goes from 0 up to n, because it's nth degree polynomial. Okay? That just follows from there. I mean, so you see that this is a general tactic. I mean, when something is given to you, first find out what is the degree of the polynomial, right? And then you can always express in terms of linear combination up to that degree. This is general. Okay. So now what we will show, in fact, is that actually in this, among these terms, there are n plus 1 terms here, right? K equal to 0 all the way up to n. But actually, we'll show that everything is 0, ak equal to 0 for k equal to 0 up to n minus 1. And then only the an survives. Okay? But that means this is a differential equation on Cn, because on the right hand side also is a constant times Cn. That's the only thing which appears. That means this is a differential equation for Cn, right? And it will be what order? Second order differential equation, because the maximum number of derivatives acting on Cn is 2 derivatives, right? So that way, if you can show this, then you see that we have obtained a second order differential equation for the Cn. So how to show this? Again, the same thing. Just multiply by, say, some Cm. So multiply by Cm times W, and in both sides, and integrate. And integrate. For m equal to 0 up to n minus 1. So on the right hand side, since we're using orthogonality, the only contribution will come when k is equal to m in this sum, right? And so right hand side gives you am times hm. Hm was a length norm square of the Cm. Right. What about the left hand side? So once you multiply by w times Cm, w cancels, and you get Cm x times d by dx acting on SW d by dx Cm, right? Dx from a to b, whatever that interval is. Again, the same thing. You start doing partial integration. Integration by parts. Sorry. Integration by parts. Okay. So one term will be the boundary term. You see, just look at it. Take this derivative here. So one term will be the boundary term. Boundary term will be what? Cmx times SW dCn by dx. But SW vanishes at the boundary, right? So there will be no boundary term from here. So this is the same as minus d by dx acting here. So a to b dx d by dx Cm x times SW d by dx Cn. Okay. Now we again do once more the derivative. So once again, you see, I mean this again d by dx I want to put there. So in doing so, there will be a boundary term which will be this guy times SW times Cn. But once again, you have SW, it vanishes, so no boundary term. So this gives me, there's another minus sign, so it becomes plus a to b dx d by dx acting on SW d by dx Cm, right, times Cm. But this object we already saw. I mean, this object is W times a polynomial of degree less than or equal to m. I mean, this statement was a general, right? That this is for any n, this is a polynomial of degree less than or equal to n, right? So in particular for m also, this quantity, since there is a division by W here, so this quantity is going to be W times some polynomial of less than or equal to m. So now you see you have W times a polynomial of degree less than or equal to m times Cn, an integral, right? But for m between 0 to n minus 1, see this will be 0, right? So this vanishes, okay, for this range, m equals 0 to n minus 1. Only thing which will not be non-vanishing is when m equal to n. When m is equal to n, of course, this is an nth degree polynomial, and that's not 0, okay? But the point to show here was that all the lower terms vanish here, right? Because the left-hand side is that and right-hand side is 0, and since this is not 0, that means am is 0. So from this entire thing, what is left over here finally is simply an Cnx. So if you take it to the other side, you see that you got a second order differential equation for Cn. Okay. So this is the main point. Next time I will analyze these differential equations for each of those polynomials. The Hermite, I mean the three classes of the Rodrigues, Hermite polynomials, Legendre polynomials, and Jacobi polynomials, and we'll obtain the differential equations for these three. And then maybe you'll see why it's the harmonic oscillator